Today's agenda is going to be pretty straightforward. We're going to do a deep dive into flexible parametric approaches. And I think to summarize that, it's really advanced techniques for building better design intent. If you were to summarize this, it's really a lot of today is going to be focused on design intent and how to kind of master design intent in a way that makes your designs more flexible, more resilient, right? And can adapt to those changes better. And so it's kind of how do I was talking to Greg about this earlier. Hyperparametrics is a good way to describe it. It's kind of the bleeding edge of doing everything you can to maximize the parametric modeling nature of Onshape. And so that's what we're really going to focus on is not just the simple stuff like in types and sketch constraints and those kinds of ways to reflect design intent, but the advanced topics for reflecting better design intent and for more resilient models. So what are we going to do today? Well, as I mentioned before, this isn't going to be the same approach that we've done where we go step by step and walk you through a specific set of features. It's going to be opening up existing models and saying, here's the approach that this model is built with, and here's why you should consider it for your next modeling project. And so we are going to show some features. We're going to discuss some features, but it's more in the context of this is a process that this design took that allowed it to be flexible in a parametric nature. And what we really want to do is highlight different processes, workflows, and the features that go with them that will allow you to really maximize the flexibility of your parametric model. And to put it simply, maximizing the flexibility of your parametric model is building the best design intent and allowing for change easily, without lots of disruptive errors as a result. And so that's really what we're going to focus on here today is maximizing that parametric capability and maximizing that ability to reflect the best design intent and have the best design intent built into your model. So before we get into it, I want to start with a simple question for the audience and something to consider as we're diving into this. And everyone has their own definition of what is complexity. And I think complexity can come in a lot of different forms. It depends a lot on what you're doing. So complexity, one person's complexity may be the sheer size of the model and the number of parts. Others might be just the mathematics of the surfaces themselves, especially in more complex shapes. The number of references, the resilience to change, all of those things can define the kind of anecdotal definition of complexity, but I think it varies for everyone. And I think a lot of what you'll find in this webinar and coming webinars is that everyone has a different approach, but there are things that we share in common. So things to think about is when you're thinking about applying the practices we're going to show you here today is what are your expectations for size? What are your expectations for complexity of shape, of the number of references that you'll need? How common is change going to be for you? How important is it to make your design resilient to change? I think those are the things you want to consider before you start the design, because it leaves you in a much more informed position to make decisions about how to structure your data after. And so, in other words, what is your intent? And I think that is an important thing to consider before we dive into the specifics of features and workflows and processes, is think a moment about what is your design intent. And it really does boil down to managing the design intent is the equivalent of managing the complexity. What you're really doing there is managing the intent of the designer so that it can handle more complex changes. And so they are one and the same. And when you're managing the design intent, you are managing that complexity. And so there are a handful of things, and I think that both Greg and I will go over examples of this in just a bit, but there's a lot of things you want to consider when you talk about design intent. And a lot of these considerations can happen before you do any design work. So a handful of things that I would ask, of the audience as you're starting your next project, are there features that require greater parametric flexibility than others? Not all parts are created equal. There may be some that require a great degree of flexibility, for instance, configured parts, or just parts that are going to need to adapt to change well. But there may be other parts that don't. And it's the judgment call as to whether or not you want to build that, take that extra effort to build the design intent so that it can handle those changes more effectively. But I think the important thing to consider is, looking at your design ahead of time and determining which parts are likely to change quite often, either because of the designs changing often or because of configurations, and which parts aren't. which parts are unlikely to change. And that will do yourself a great service when it comes later on to defining where the extra energy should go. What features or parts are geometrically dependent on each other? That's another important question to ask yourself, because as you're starting to design, especially as the examples Greg and I will show you in just a bit, multi-part part studios are very common occurrence. They're probably one of the most popular techniques for reflecting that design intent. And you really do have to ask yourself what parts belong in a single part studio, what parts belong outside of that part studio, what parts have no contextual relevance to other parts. And that's an important thing to consider when it comes to not only your design intent, properly reflecting that design intent, but also organizing your data. Having everything in a single part studio is just not practical for a lot of different reasons. And you'll have to ask yourself, well, what makes sense? What features are related to each other? And I say parts because in Onshape, we can design multiple parts together. And so it could be in the context of parts as well. But that's another important consideration. What is the best way to organize your data? And this is something that Greg is going to go into a lot more depth on, because he has lots of great examples of this. But it's important when you're designing anything that is in a team environment, for example, is you really want to structure your data in a way that's easily understood by others. And organization is a big part of that. Not only understood by others, but even understood by you, perhaps when you're coming back to it a year later. So how do you structure the data? How do you name the data? What are the best approaches for organization that allow you to understand what's going on there, right, in that particular part studio?
Just a little important point here too as well. All the examples we're going to show you have been created in the past, or the shapes have been created, or the images have been created in one form or another, even back to a century ago by hand on a piece of pencil on paper. So we're not going to show you things that have never been able to be done before. It's the approach which is really important, right? And Onshape has specific superpowers in a lot of this when it all comes together. So just wanted to get that out there. It's not where we're trying to say that Onshape is the only one who have ever created this shape. That's not what we're saying. But what we will show you is that Onshape has some specific key benefits to the approach you take to achieve the goal.
Absolutely. Yeah, and that's a lot of what we're going to focus on here today. Isn't so much the individual options, but more the broader approach that's used to structure data, to communicate your data, to reflect the best design intent. So that leads me to the next one. How do you communicate design intent to your team? This is going to be an important one because, as you know, if you work in a team environment, it can be very difficult to dive into someone else's model and understand what they've done without a serious amount of time. And I think that the closest equivalent that I can give you, if you're familiar with software development, is kind of commenting out your code to explain what each of the functions are. And that's really an important concept, not just in software development, but hardware development as well, and CAD as well. You really want someone to be able to dive into your design, your part studio, and be able to understand what's happening and why it's happening, and have a clear understanding of what the original creator's intent was. And a lot of that is incumbent on the original creator to define that. And so we're going to show you some techniques and some just tools that you can use that really make that easy to communicate with the rest of the team. Here's my intent in structuring the data this way and using this particular design intent. And then one very important final factor to consider that I think a lot of people overlook, at least at first, is how do you plan to manufacture or assemble this part or series of parts, right, at this project? And I think that this is something that's often an afterthought, but that should be considered before you begin, because it often reflects in your design intent, in the features that you choose, the order that you choose them in, the delineation between features can even be defined by how it's going to be built or how it's going to be assembled, right? And so if you've heard the phrase, DFMA, design for manufacturability or design for assembly, this is kind of the precursor to that. This is where you start, is in the early design, intent phase where you're considering how this is going to be structured. Think about how it's going to be built, and try to reflect that in your design intent, in the tools and the features that you use to actually build it. As we have a handful of examples of that as well. So what I'd really like to do is dive into it. and show you some examples. I'm going to start with a handful of very basic examples, then I'm going to pass it to Greg. Greg has a whole bunch of really awesome examples to show you. But as I mentioned before, keep in mind this is going to be a little bit different. We're going to jump from example to example and highlight the things that we think are best about it in terms of its flexible parametric nature. Now, before I begin, I want to open things up. So if there's any questions, please feel free to type them in the chat. If you're interested in talking to an Onshape representative, type +1 in the chat, and we'll reach out to you. An Onshape representative will reach out to you. Also, as we're diving through things, as I mentioned before, we're going to be covering things kind of at a superficial level. We're just going to barely scratch the surface of a lot of different topics. If you're interested in a deeper dive into any one of these topics, feel free to type it in the chat. One of the things that we're looking for in this new webinar series is feedback about what you'd like to see. So please encourage you, use the chat, give us any feedback you'd like, ask any questions you'd like, and if you'd like to hear from an Onshape rep, type +1, and we'll make sure to reach out to you. All right, so I want to start with the dump trailer, and I'm starting here because I think it's a good, well-rounded example of designing a complete project in Onshape, and it uses a lot of the flexible parametric approaches that I would recommend if you're going to design any kind of project of this scale in Onshape. It uses, most importantly, multi-part parse studios. That's a continuous theme that you're going to see. One of the biggest methods, the strongest methods for creating proper design intent is just to simply model parts together, that should be designed together. And I think that if you're not using multi-part parse studios to the advantage of having that better design intent, you should start today. I think that's tip number 1. But I think that involves a lot of different layers and facets. So it's not just designing multiple parts together, but it's the tools that you use to accomplish those multiple parts. And in particular, there's a handful of techniques that I would say are really used by power users trying to get the most out of their parametric models. And the first is a skeleton-driven layout style sketch. And you'll see that commonly in lots of different top-down design structures where you have a single sketch that drives multiple parts. And the reason this is advantageous, obviously, is you don't need to make these things together. You don't need to go in and define the relationship relative to each other. They're modeled relative to each other with all the proper dimensions and constraints in the sketch. And that is tremendously powerful. So if you're not familiar with the concept of laying out a sketch, or sometimes referred to as skeleton sketches, it's a very common technique, very popular for maximizing parametric or design intent. Right? So you have the ability to define that. Now, the last thing I would point out in this is the use of folders. And you're going to see me talk about folders at different points. But I think folders are probably one of the most effective tools we have for conveying to others our design intent. And this is a great example of that. So I'm going to jump into it. Bear with me for a moment here. We'll switch over to the dump trailer. And here I just want to start with a simple introduction and explanation as to why I think this is a great example of a full project done using lots of great top-down, robust parametric modeling techniques. And the first isn't actually the modeling techniques themselves, but the folder structure. And so you'll see there are folders for each of the subassemblies, the dump subassembly, the base subassembly, the frame subassembly. And so as a person who's coming into this who didn't model it, it's very clear to me what these folders contain. And I don't have to hunt for the parts studio associated with the hydraulics. It's in a folder called hydraulics, and that makes it very clear. And I say this, this is useful if you work with anyone else because they have a very clear understanding of what you're trying to do. Now, the folders apply not just to the tabs in the document, of course, but also to the individual features, right? And so, as I switch tabs here, what you'll notice is that the way the parts are structured allows for really effective communication. I've structured the folders according to the features that are associated with them. So the top plates in this dump base part studio are all built together, right? And you can see in this case I have 50 parts or so built together, relatively simple frames and sheet metal parts, but they're categorized in a way that allows me to easily understand what the various folders contain. So front plate, top plate, rear plate, frame, and each one of these is very simple. Now, throughout this document, throughout all the different examples that I'm going to show you, layout sketches are persistent, and that's because they're so effective. So the frame in this dump base, it's laid out with a layout sketch, one single sketch that drives many different parts. In this case, probably about a dozen different parts associated with the frame. But that's just one example where I think that's really relevant. But layout sketches are persistent. So if I go into, for instance, the axle, let's drive into the axle, you'll see that there's a single layout sketch that drives almost the entire suspension associated with this axle, from the leaf springs to the U-bolts to the hangers. Everything just about is defined in this, let me go ahead and bring it up, this particular layout sketch, right? So in this case, it's just, again, another example of a single controlling layout or skeleton style sketch that's driving multiple parts. In this case, the simple leaf springs, but also the hangers, the U-bolts associated with the dimensions associated with them. And so you're going to see that single controlling sketch affects, in this case, probably another 8 or 9 different parts. And so this common technique of using layout sketches to drive overarching geometry, even the entire project in a lot of situations can be driven based on a single layout sketch, makes them extremely powerful. And also means that you have one place, and sometimes even one variable or one dimension that can have a dramatic change on dozens of parts, if you've built it in a certain way. So if I were to extend the length of these hangers, and the leaf spring would naturally get longer, right? If I were to extend the width, all of these parts would change at the same time. And I think when we talk about maximizing parametric approaches, layout sketches and multi-part part studios are kind of the killer combination for building really flexible parametric design. So that's my first example. Let me dive into my next one here. And so what I'd like to get into is configurations. And I remember showing this to Greg, and he's like, is this really complicated enough? And bear with me for a moment here. It's a simple part, admittedly. This is a simple part. It's an ANSI B16.5 pipe flange. But for those that do any kind of pipe design, you'll know that there are thousands of permutations of this particular pipe flange. And so while the geometry itself is rather simple, it's just a cylindrical boss with a hole in it, there's a great deal of thought that goes into building the configurations that are associated with this pipe flange. Now, what's really neat about this pipe flange is if you want to follow along and try this with me, you can. If you go to onshape.pro/try configurations, there's a public doc of this model that you could walk through and experiment with and make your own copy of and really kind of understand what I'm about to explain to you in a little bit more depth and play with it yourself. So I encourage you, if you're interested, you don't even have to have an Onshape account in this case. Just go to onshape.pro/try configurations and you can open up this model and play with it. But as I mentioned, it's not a complicated model in terms of its geometric complexity. But going back to the slide earlier, a lot of complexity comes in the form of how it's made, and more importantly, how the design is structured. And I say that because in this particular case, in the ANSI B16.5 pipe fitting, it has lots and lots of possible permutations. And the permutations aren't necessarily like this linear growth of any specific dimensions. It's a lot of different values. So at this pressure rating and this nominal size, this is the outside diameter, and this is the inside diameter, and this is the bolt pattern used. So it's a lot of kind of different values that are stored together. And so I want to take a moment to explain how you could accomplish something this complex using essentially 4 configuration inputs. And so for those not familiar, in Onshape, we can create independent inputs in our configurations. You don't need this massive Excel spreadsheet with several thousand rows. The way we handle things is you have these independently controllable inputs. And so I have inputs for every nominal size that exists within the standard. This is a standard conforming part, I should say. So all of these values are being pulled from a book, right? And so in this case, I have nominal size 2 inch. I have flush face and not. So I can say, okay, this is a flush face or not, right? Very easy to make those changes. I can define the style, so I can say this is, a weld neck flange rather than, a slip flange, and you can see it adds those defining features. What's really most intriguing to me about this isn't necessarily the nominal sizes or anything like that, it's the pressure rating. Because the pressure rating really defines on a pipe fitting flange all the different dimensions that are associated with it. So a 2 inch pressure rated at 300 has a totally different bolt pattern, has different thickness, has different dimensions than the 150. And so in a traditional system, if you wanted to capture all of that design intent, you'd have to build a table with every possible permutation listed in. But in Onshape, we can build some really clever expressions that reflect that design intent in a much simpler way. And so I could say, okay, well, this is a 150, but what if I change this to a 300 pressure? Notice what happens is the number of bolts in the bolt hole pattern changes from 4 to 8. Because the pressure has gone up, I need more bolts to hold it together. It's a natural thing, but that's all coming from, remember, from a known database of all these sizes. So how do you accomplish this? Well, it uses a combination of variables and expressions to do some really neat things. So the first thing I would stress is it has this variable called class. And if I go into class, you'll see how it's defined. And I've stretched out the dialogue here a bit so you can see the entire expression. But if you can't read it, just keep in mind that it's basically boiled down into 4 groups. If the pressure is less than 150, it's class 0. If the pressure is less than 300, it's class 1. If the pressure is less than 400, it's class 2. If it's less than 600, it's class 3. And if it's over 600, it's class 4. Now that's just defining that this class number is driven by a pressure rating. And so when the user types in a pressure rating, it's going to automatically assign to them a class number. The way this is actually consumed is by using what we refer to as arrays. And so if I go into the configuration table, configuration panel, I see the flyout with all my different configuration inputs. What I want to point out about this is just how many arrays are in each one of these values. So I can see that I have nominal size, outside diameter. And in each one of these, I have a handful of values. Each one of those correspond to a class. So when I say it's a 300 pressure rating, well, that tells it it's a class 1 pipe fitting. And if it's a class 1 pipe fitting, it's the second value. It's not 0, it's 1, which means in this case, in a 1/2 inch, a 3.75. And a 2 inch, you can see it's 6.5. So the diameter actually gets larger for a pressure 300 rating. And when I go all the way over 600 pressure rating, the diameter, the outside diameter grows to an 8.5. And so that array is just linking to class values and saying for every change that I make to the pressure rating that moves the class, make sure all these values, the outside diameter, the thickness, the number of holes, you can see there's an array controlling the hole pattern and the number of instances associated with that hole pattern. All of that is controlled with what is essentially just one table. One table with the number of entries for each size. In a traditional system, you would have to create hundreds or thousands of rows in a table to accomplish the equivalent of this. And it's not going to be as flexible. You won't build as many combinations. There's more possibility for error. So I'd just like to stress that the thought process here is using expressions, in this case, an expression to define a class. That class pulls a whole bunch of different values for diameter, thickness, holes, bolt circle patterns, raised faces, everything that you could want to configure associated with this pipe fitting is here and configurable via these array lookups. They're just looking through the different values in the array and pulling the right one based on its class. And so again, this is a publicly available model. I encourage you to go check it out if you're really in diving deep into configurations or parametric relationships. The maximizing design intent is the way that I would represent this or say this. I really encourage you to take a look at this because it's a great example of what's possible with our configurations, variables, and expressions. Now, my last example, I'm going to jump back to my slide just briefly, is I want to go over one more example of using variables in configurations. And I want to show this because it's a commonly asked question. And it's one that I think a lot of users have reached at some point in the design, especially if designs you expect to change often, whether it be for configurations or just because you're doing a lot of experimentation. And that is, how do I do very basic, like if-then statements in a dialogue, right? So they say that if this is set to this, then I want you to set this value to that. And you can do that inside of Onshape. And in fact, is one of the biggest tips that I have for you throughout this entire presentation is the ability to use to maximize the expressions in your features to reflect the best design intent. I know Greg's got a whole bunch of these examples as well, but if I were to point to a single set of tools that can really level you up in terms of power users and maximizing design intent, expressions would probably be definitely high on that list, if not number one. So let's dive into a quick example of this, and I will be brief, but in this case, we have a configurable chassis. It's just an enclosure. Maybe it's a network attached storage or some kind of computing box that has lots of USB inputs and lots of HDMI inputs and power in the back and Wi-Fi antennas and all these different pieces. And what I really wanted to do here is build a configurable assembly so that the user could come in and say, no, I want, let's say 5 USB ports, and it will regenerate, and the model will parametrically update the entire geometry, the sheet metal housing and everything, will parametrically update to accommodate just about any configuration that the user would want. And that's really the intent behind this data set. Now, what's unique about it, and what I'd like to point out, is the way it's built. The driving factors here are the things that I care about. The design intent starts with the HDMI port, the Ethernet port, and the USB port. And then I build the sheet metal housing around those factors because that's my intent. I want them to be able to configure those things. And then I can build something that dynamically updates to that number. But where it really gets tricky is when you start to define things that change based on something else. And I use the kind of if-then description to define what I mean by this is, let's say, for instance, that as the number gets bigger, say the number of USB ports gets bigger, well, that means this thing is naturally going to get wider and wider. And as it gets wider and wider, the volume inside of air changes, gets bigger and bigger. It means we need to go from, let's say, 2 fans to 3 fans. Well, in this case, there's actually logic built in to change the number of fans. You see the fan cuts in the back, by the way. So you see the slotted cuts in the back. Those are the mounts for the fans. And those fans, the number of them will change depending on the width or the number of USB ports. So I just changed this to a 3 USB port configuration. And you'll notice that now the 3-port USB port configuration only has 2 fans. And that's because I've created a rule that says if the number of USB ports is greater than 3, increase the pattern count for these cuts to 3, right? And so what I'm saying is if this number is 4 or more, make sure that you have 3 fans instead of 2. And I bring this up as an example because it's one of the most common questions we get when we talk about design changes is how do I make these relationships, these complex relationships that depend on values or dimensions, how do I make them relative to each other? And I think that expressions are one of the easiest ways to accomplish this. So I'm going to go down into linear pattern. I just want to show you the expression used to generate this. So this is just a linear pattern of that circular cut for the fans. And if you, at first glance, look at it, it looks very similar to any other linear pattern. So you have features to pattern, you have a direction to pattern along, you have distance. What's really unique about this is the expression used to define the number of instances. And so if I select the instance count, you'll see the actual expression used. And it's hash symbol USB ports greater than 3, question mark 3, else 2, colon 2. And so the way to interpret this is the variable, configuration variable USB ports, if it's greater than 3, then this number, this value, should equate to 2. If it's not greater than 3, it should equate, or excuse me, it should equate to 3. If it's not greater than 3, it should equate to 2. And so these two are the potential values for the instance count, and this is the expression used to define the total number of instances based on another factor, in this case, USB ports. And I'm going to leave this up on the screen because this is one of the most commonly asked questions, and I think adds a lot of power to any kind of feature counts or dimension values where you define based on a certain factor. Another example I would give, and this is something that I've had come up with a user, say I'm designing a trailer, and the longer the trailer gets, the more pattern instances I would expect in the change in geometry over time. And this is another way you could accomplish that, modifying that pattern instance based on the overall length. If it's greater than this, it should be this. And I showed you an example of that in the pipe fitting. just a moment ago, a really elaborate expression that said, if the pressure is less than or equal to this, it's this, if it's the, and you could build these really to be quite elaborate. But in the simplest form, if you're just trying to say, if a value is bigger than this, use this, else this is as simple as it needs to be. And I really encourage you to, if you're trying to get the most out of your design and not have to manually edit features and change pattern instances and so on, maximize expressions is probably one of the biggest tips that I have for you. So that is what I had planned. And now I'm going to pass things over to Greg.
Okay, thanks, Cody. I'll share my screen now. So a lot of what Cody's been talking about, and of course, the real theme of today is intent, right? And sharing your intent, defining your intent, capturing your intent. And, the best way to do that is to be organized. So, I'm not going to go through all this list here because the examples are better for that. But, I've listed some of these things which Onshape really helps you do to get organized. And, I'm going to show you a bunch of things to do with setting colors on sketches or curves or faces, making sure you create folders and name them, designing and thinking in sort of functional blocks, all of these things. And again, Cody's shown you some great things about variables and expressions, but this whole list is really at the core of this capturing of the design and intent. So the first example I want to show is my favorite Nitro engine. This is an old an engine for a radio controlled car. And, the real question about this is multi-part part studio versus assembly versus lots of parts, lots of part studios. Let's try and address some of that right up front here. So you can see actually it's got a lot of nice parts on it if I cut the cross section through here. So clearly this needs to be an assembly. But the first sort of chicken or egg question that might get asked is, well, how much do you put in a single part studio versus separate part studios? And the answer, of course, is it depends. And it depends on your intent, right? You could do a lot of these things in a single part studio because this is not a crazy number of features or crazy number of difficulty of topology. But what I have done is one way to approach it here, and that is to isolate a key component, which is the crankcase, and then have a look at the things that are directly touching it and sort of the functional areas of it. And what I've done is I actually modeled these things in three real big stages: the core features, the casting features, and then the machining features, which is exactly how you would think about design for manufacture, right? And the design for assembly and the functional design of this thing to start with. So when I say core, I'm going to isolate them and show you that I created these features as solids first. They're not actually, they're multi-parts in here. One of them represents the exhaust port, one of them represents the cylinder and the ports around the cylinder, and one of them represents the intake and everything that's going to go on the inside. So I can allocate variables to these, and you can see here I've used a variable studio for top level document wide variables, as well as variables that are specific and local to the crankcase itself. So variables and variable studios are a key part of this getting organized theme. And those variables are driving these core things. Now, there's a number of other ones that are important too, and that is where you have bought-in components. So there's an R6Z bearing that goes in the front here, a sealed bearing, and then there's a 6902 bearing inside of here. These are things that I don't need to model as part of this part studio because they're an established standard, right? So the outer diameters of those are going to be core. So that is one way that I can sort of say I'm going to draw the line as to how much I model inside a single part studio. The way that I've done this then is that after I've created these core features, and you can see again it creates multiple parts in here. I'm actually not going to ever ship these parts or manufacture these parts. These are purely for sort of functional development. But later on you'll see that there's a big Boolean feature, which is where I subtract those core parts away from what I had been creating, which is the casting, this investment casting or whatever the casting process is going to be for this. So I don't ever throw these tools away. This is also a little bit of a tip, because it makes for some nice eye candy for looking at later on, but it also it helps me doing measurements and all sorts of other things like that. So keeping these tools in here, whereas the part that I'm actually going to put in the assembly is the actual is this one here. Final word on this, other than you can see that I've named things and I've kept things nicely arranged in folders, is that anything that's going to be touched by a machine is red, right? So I've created those colors, and there's actually a really nice way to do that. You just right click on a feature and say add appearance to feature, and that's a nice little tip to keep things organized in that way. Now you can choose whatever color, of course, that you decide makes sense for you. All right, so that is my first example there. The next one is a cylinder head. This is a pretty complicated one because there's a lot of variables and there's a lot of design for ... kind of considerations that need to be made from both the casting, the manufacturing, the functional, and you might actually, as I've suggested down here, want to be doing some simulation along the way, sort of using design-led simulation or simulation-based design. So let's delve into this one because it's a pretty fun model to have a look at. So just to show you, this is an outcome. If I cut through it, you'll see that it's pretty complicated on the inside, and there's obviously a repeating unit, which I'll make very good use of. And of course, this isn't the final cylinder head. This is in the conceptual stage or the model building stage, which I wanted to show you because this is the really key part, and this is where you get the benefit. If you can think up front, rather than just think of the final shape. If you try to think of the final shape and then just model all these fillets one by one by one, it's just going to be a little bit of a nightmare. So let's break it down into the constitutive, the parts here. So this is the repeating unit of the combustion chamber, the valves, the inlet and outlet ports. And the way that I've done this is similar to what Cody has talked about before, is with a lot of very important layout sketches. Now these sketches, which have been defined up here in the layout section, contain the very core things like the bore diameters, the valve offsets and angles, and you can see all those are related to variables again as well. Some of these are calculated with expressions, ratios here and there, and I build a lot of these calculations into the variables with expressions just to make sure, as a little bit of a design check as I go along, make sure that the volume of the cylinder, the combustion chamber, is not getting beyond a certain limit. I have those expressions built into here, and so that I can keep a check on that. With respect to these sketches in here, these layout sketches, you can see that I've used colors. Hopefully they show up well for everybody. And I've used colors that are appropriate for my eyes. And you can see that on the intake side, everything's green. You can see here, this is the, and if I highlight there, you can see this is the intake port spline that I'm using to show the shape of that. So not only I've named it nicely, but I've also colored it. I know that everything green is on the intake side, everything on red is on the exhaust side. It's impossible to keep track of so many complicated sketches unless you use some very, very rigid and diligent scheme for these kinds of things. And in the end, I've created a bunch of parts in this multi-part part studio. You can see here I've created the combustion chamber, the inlet ports, there's some clearance for the spark plug, and then the really difficult part is the blue stuff, which is where the coolant is going to go. And the coolant is offset from a lot of these things, and you can see how it makes sense to do things very, very closely topologically related. That is one way to do it. The other way to do it is to take a multi-part studio approach where you end up with ultimately the same end result, right? And actually, what was really interesting is if I have a look at the regeneration times, about 8 seconds for this, and there's 300 features. So it's a decent size part studio. well within our guidelines, for what you should expect for performance. In this case, if I have a look at this part studio, which is the final slice, you'll notice that it's really fast. It's just over a second. And the reason for that is that I have used version references and derived things in. I've derived stuff like those cores for the ports and the cores for the combustion chamber. I've derived them into this part studio and then done my Booleans at that stage here. So again, this is the intent and question mark and it depends is always the answer to that. And the reason I did it this way is that I'm making a lot of changes that are going to be potentially for just at this local level, and I don't need to regenerate everything that went into the combustion chamber or these complicated ports and lofts that are in there. I don't want to regenerate that every time. I just want to regenerate the bits that are here. Perhaps I'm doing some simulation and I'm looking at just these particular fillets. So splitting things up, there's no right or wrong way. Well, there's wrong ways, but there's not good ways. But in this case, whether I do it in a single part studio with lots of carefully controlled references, or multiple part studios where in this first part studio, you can see I just had a few datum planes, a few of these sketches, and a couple of keep out zones, and that constitutes all of the layout which is going to go into these other steps. So that's a pretty interesting one. The next example is this chair. All right, so some of you may have recognized this chair. It's a pretty common or famous one from the Bauhaus, almost exactly 100 years old, I think, this design. This is a very good example to use skeletons to drive the shapes, right? And expressions, and something else I'll bring in here, which is a measured variable. So let's go back to this and have a quick look. So the assembly of this chair is nice. And if I just show you a couple of things that introduce complexity, is that there's a lot of offsets that are simple, and then you think about them and say, oh, actually, they're not so simple after all. And you want to get these things right so that the holes line up. Sorry, I just overshot there a little bit. You want to line these up so that in response to change, whether that change is intended because you're going to release a family of things, or you just want to have a resilient, robust model, which is always a good idea anyway. They're not as simple as they look. All right. So let's have a look at the part studio that created this. And I'm going to draw your attention to the purple big blob and the sketch, these red sketches. Now, hopefully they show up for you as well. So these really define the overwhelmingly driving dimensions for this chair. Right? You'll see it height, width, depth, and the front depth for the cutout and the rear depth for the cutout. These are the things that probably appear on the specification sheet if you go to the catalog. These are the things that I'm definitely going to assign variables to, and I can flex this thing obviously in milliseconds, right? To create, it's a very, very simple model. But simple is good in this case because I can make it overly complicated too soon. That's a trap. Right? You want to keep things clean. You want to keep things simple so that they respond resiliently to change. So the way that this then worked, this part studio, you see I haven't modeled all of the parts because that's in the assembly. You'll see down here, if I turn off the parts and turn off the composite parts here, that I created these blue routing curves. And the blue routing curve is actually using a new custom feature we've created called routing curve. And this is a very convenient way to define the path for the frames that are going to come in here. So you can see here we've got a routing curve. The routing curve is then now going to reference the vertices of those sketches, those driving sketches. And that's the key to it. The bend radii in the routing curve, they are being referred to variables. So it's all, it's following all of these guidelines. Use expressions, use variables, use colors. The blue things are always the routing curves in my own definition. And then from that, then you can create the frame feature, which is something that's a very strong, powerful tool set in Onshape. I can just use that single routing curve to create the back frame, a single frame feature to create the base frame, and one more to do the seat frame. That is, a really efficient way to make this thing resilient to changes as well. So even though I'm going to hide this now, even though this chair only comes in one frame size, which is 3/4 inch, I've actually created a configuration so that I can update this configuration. And you'll notice that they fits together perfectly, right? It always fits together perfectly. Everything updates resiliently. And you can see why, I think it was Marcel Breuer didn't design this thing with 1.5 inch tubes. He designed it with 3/4 inch tubes. But having it with the ability to make these changes really rapidly is always a very good thing. Now, just quickly on this last one, I won't go back to the PowerPoint because I think we can just jump straight into it from here. This is one of my favorite models here, which exhibits what Cody and we were talking about before, which is hyperparametric modeling, which is, as a bit of a fun title. I don't think there's an official scientific definition for that, but it's one way to describe it is making things overly parametric, even if you didn't need to, right? And in this case, I don't need to create multiple configurations like that pipe flange. I'm actually just releasing a single design of this. But what if I could make this so resilient to change, the swept back angle or the dihedral or the washout or the thickness of all of these, all of these members in here. And if I take a cross section through here, you'll see that, this is very, very detailed modeling in here, and everything does fit perfectly. All of these miters are perfect, and all of these components, if I just highlight that, you can see how the cutouts on the front, the leading edge and the trailing edge, everything was done perfectly. No, there's nothing left to, whoever's putting it together can just adjust to taste or to adjusting. This was an exercise in how parametric and how robust can we make this thing. And one of the really key aspects to doing this is creating patterns of features or as patterns of parts that respond very well to outside influences. So, if the outside influence for this, again, would be variables, and the variables being the sweep back angle or the chord length at the root versus the chord length at the tip. And of course, if I start changing those things, then all of the ribs and all of these intermediate diagonal ribs will also have to change. That is the key challenge for this in here. And actually, it's worth noting for a second here about document structure as well. Here, I've got a single document which has a number of things in it: part studios, drawings, some reference images, some renderings that I was doing here before. And I'm modeling the fuselage in this document as well. The wing is actually coming from a second document. You can see here that it's actually showing you that it's linked in from a different document. And that is a very good option to have at your fingertips. Different groups working on different things. Maybe there's a different release scheme or release strategy that you're going to have with components or sub-assemblies which have a different sort of cadence to them. So here in this fuselage, I can focus on creating, getting the electronics right, getting the wiring right, and all of those things. Whereas the wing document takes care of itself, and then I can incorporate it when and where and update the versions as things change. You can see here, actually, there's a new version of that wing available that I could update. Quick note here on colors. Decals also a very important thing. You see how much realism and it adds a level to it Now, even if it's not just putting a manufacturer logo onto it or some other person's logo onto it, it's a really good idea to use colors and even decals to remind you of certain things, like this is the intake side, or this is up, or you can do all of those sorts of things even as temporary measures, just so that you can manage your complexity in here, just so that it's absolutely clear and you don't end up putting something on the wrong side of where it should have been put to start with. Now, I have an example here as well, which is very, very similar in concept to those ribs in the wing. And this shows an interesting use of patterning in Onshape, which is one of the hidden superpowers. So in this particular guitar, and if those of you who have sort of heavy metal fans might recognize, the frets on this guitar board aren't straight or sort of perpendicular across. There's a very interesting pattern, and they're called a fan pattern, right? Or the fan frets here. So being able to capture the intent of this is a really, really key, powerful thing that we can do. So just like Cody showed before, I've got a number of inputs to my configuration, the number of frets, the length of the strings, which will affect, sound, of course. There's a lot of expressions in here to determine angles. And then there's this really, really interesting pattern, and I'm not going to get enough time to explain fully into this, but you can see here I'm doing a feature pattern, and these are all of the features that are participating in the pattern. And obviously there's things being driven by variables from the outside, and really, really important button here, which is to reapply features, which is recalculate the topology as we go down this pattern. Now, in computer language, this is essentially the same as doing a for loop, where I've got I equals 0 to 22 or 1 to 22, and I'm doing my calculations over and over again inside of a for loop. And it's just a lot more friendly, though, to be able to do this graphically in the way that we do it in Onshape. So I put that out there without further explanation, and something that's worth deep diving into at a time in future, to explore how these advanced patternings can really take care of a lot of the automation and capture your design intent. So that, Cody, I'll throw back to you.
Awesome. Let me share my screen. So a few things that I really like that you showed. The first is colors. I think that's the probably coolest tip. It's an easy one, but to isolate the machine features by colors is a really cool way to organize the data and make it easily discernible by someone who didn't necessarily model it. But to me, I think the biggest thing that I took away is I think a lot of people, myself included, tend to think of layouts as sketches. But in your example, you're showing these as solid parts that are used and then derived in and using versions. And what's really compelling about that is it's 3D geometry, modeling around 3D geometry, but you kind of isolated the things that don't really change that often from the things that are going to change a ton, right? And I think that notion is what I would describe as someone who's really strong with understanding their design intent, is they know I have some things that I just have to work around that are off the shelf or whatever it may be, and I'm going to take those, model them, and then derive them in using versions so they don't regenerate constantly, right? And then I model around those things and I make all the changes and do all the flexible parametric stuff around the things that I know need to change often.
Yeah, absolutely. The other aspect of that is also that surfaces could be used as you can use solid as layouts, but you can use surfaces as well. And surfaces as a layout is a really, really key concept for interface management. So the interface between things doesn't change, right? And it's sometimes it's a given. It's like a USB interface or a power outlet. So those interfaces are set and standards. So you want to use them wherever possible. And in my Nitro engine example, the interface, one of the interfaces that I did use a surface layout for, was where the exhaust pipe muffler connects with the engine block. Now that isn't going to change because there's aftermarket exhausts that go on, and so the interface is really long-lived, right? There's a longevity in interfaces which you can capture. Yep.
And I think that kind of reflects on knowing the things that are fixed versus knowing the things that need to be flexible. And it's kind of the forethought discussion that we were talking about earlier, is thinking about those things ahead of time. And you can really even optimize for performance when you consider these things. If you're deriving in versions that aren't being regenerated constantly, you really have a quick model, which is what you showed there. So I want to do a brief recap into a handful of tools that we discussed, because I know we really covered these at kind of a superficial level. We just scratched the surface into a lot of tools. And what we're really trying to do here is to stimulate you to go try some of these features out and start to incorporate them into your next design if you're really trying to build that robust model. So just a brief summary of some of the tools that we've discussed here today. Obviously, multi-part part studios are a big part of it. So almost every example we showed had them. Even if you're using assembly context, you're probably using multi-part part studios as well. It's kind of the core of really robust parametric modeling. But variables and variable studios are a big factor in designing with better design intent. Because they just really allow you to reflect your design intent in a lot more intuitive way. Configurations are configurations. If you need them, you're going to need to know how to build good design intent. That's an important prerequisite to building really robust configurations. So if you're in that camp, you know it, and a lot of this stuff hopefully is good practice for you to take into your next design. If I had to point to really one power user level function that I would point out as being really useful for building robust designs, is expressions, because they allowed you to build those relationships really quickly and easily, and make the design much more flexible to change. You can really build the model that changes based on a handful of factors and updates thousands of dimensions in theory. So you can really do some powerful stuff with expressions. Measured variables, another one that Greg mentioned, that's really a powerful one. Skeletons and layouts, I think one of the most common techniques, any kind of layout. And as Greg showed, it doesn't have to be a sketch. It can be underlying curve geometry, solid geometry. You can use derives and versions to speed up the process and isolate the things that don't change that often. So there's a whole technique, and we could probably spend a whole day, or a whole webinar on just layouts, because they're such a complex topic, but they are incredibly important to what we're talking about here today. Also advanced patterning, like the fretboard that Greg was showing you, just knowing that those things are possible in the pattern features is something just we don't find a lot of users using, and it's extremely powerful. So think about that. Think about applications where you might use some of these more advanced patterning, like patterning the variables and things like that in the features themselves. Derived parts, that's what Greg was showing you earlier. I think layouts are incredibly valuable, and deriving them, it isolates the things that change from the things that don't, and really makes a lot of sense. And version references, I think version references just prevent the constant regeneration of geometry that you don't really need, that doesn't change that all that often, and it speeds things up. It makes it cleaner and easily understood as well. And then there are a handful of things around organization that we want to highlight: folders and colors and decals. These are the two that I would really stress. When we talk about design intent, it's one thing if you understand it. It's another if it's so easily understood by everyone because of the way it's been defined. And folders, colors, decals, all of those things make it really obvious, not just to you, but to everyone who could be looking at this thing, that this is the intent behind these subset of features, this part, whatever it may be. So those are just some of the tools that we discussed here today, and all of this kind of surrounds the notion of really building strong design intent. Now, the last one that I would spend a little extra energy on in all of these is design for manufacturability or design for assembly, because as Greg shown, if you think of that ahead of time, you can save yourself a tremendous amount of time spent just creating duplicate features or a rework, because the features were never probably designed with assembly or manufacturing in mind. So think for a moment, how's it going to be manufactured? Were the processes machined processes, cast processes, injection molded? And how does that define the type of features that I'm going to use and the way that I use them? And having those kinds of considerations before you begin designing can have a big impact on the choices that you make while designing. And I think that's the big takeaway. And in general, I would say, just to summarize today, I know we're just a minute or two over, flexible parametric modeling is really mastered with adequate planning and forethought. And that's a consistent theme that we've seen throughout this. The correct combination of processes and tools, a lot of which we've highlighted today, and diligent organization of that data. So if I were to summarize our presentation here today, I think that sentence would best describe how to maximize flexible parametric modeling. So with that, I want to say thank you everyone for joining, and have a good day.
Thanks everybody.